Yeah, can you all see it and hear me?
We can hear you very well, and the screen is appearing to the audience. Okay, it's perfect now. We can see you, we can hear you, we can see your slides.
Great.
You can
Thanks
start.
for the intro. Thanks everyone for coming. Like to tell you about Wassersplines, this tool I think enables a really exciting form of animation. So here's a pretty basic outline. I'll try to motivate the problem relative to traditional articulated animation, then formalize our approach and solution to the problem, and then I'll conclude with some takeaways. Here's a typical animation pipeline for articulated objects, meaning things with skeletal structures, where you start with a mesh, build a rig, meaning a skeleton for it, and then puppeteer the rig to create animations. And it's a really well-established method with a huge amount of learning resources, making it very accessible. For example, I made this pretty basic model after just watching a couple YouTube tutorials. And so that's really great. But there is a key limitation that it requires there to be a skeletal structure. But not all animations have articulation or skeletons. For example, the Droon in this Disney movie are these malicious miasmic creatures with no well-defined form or structure. They almost behave like fluids, except for the fact that they don't actually care about things like the Navier-Stokes equation. They just sort of have to slosh between keyframes to convey their like ominous character. Then in the Terminator 2, there's these futuristic robots that are made of liquid metal, and the robots themselves are articulated, but the transformation from amorphous mass to the robot is unarticulated. And it's not something you can do with a rig or a control cage. And then this type of thing happens even before computer graphics. This is a shot of Cruella's cigarette smoke in 101 Dalmatians. It has this wispy, twisty, space-filling curve-like behavior. And there's clearly no rig, but it still needs to hit certain key shapes to convey the twisted personality of Cruella. So the things these examples have in common is there's no articulation, and they have to be artist directable, meaning they hit the specified keyframes. In my opinion, this kind of animation sits somewhere between visual effects and character performance. So I'm going to call it unstructured animation. And this project really aims to make it easier to create this type of animation. To formalize the problem, we'll start by representing keyframes as probability measures, because measures have no topology constraints, and they're fully capable of representing mesh-based things as normalized indicator functions. There's a bit of a technical detail, but we really mean measures with sample access, meaning we can draw points according to their distributions. And this is a weaker requirement than density access, because we don't actually need to know what the density values are as long as we have a method of obtaining points. And then the interpolation, the animation is going to be built from this velocity field, f theta. And from the title of the talk, you can probably guess that theta is going to be the weights of a neural net that computes velocity field values. And this parameterization gives us some really nice benefits I'll talk about later. But for now, I'm going to leave it vague as f theta. So you could also imagine choosing theta to represent your favorite FEM basis functions, and nothing here would change. I'm going to denote phi superscript AB as the map you get from integrating the velocity field from time A to time B. And this definition allows us to use the following push forward measure notation. If you're not super familiar with it, the pound sign is intentional and is how you denote applying phi to a measure. So if x0 is the starting keyframe, then the result of flowing x0 through the velocity field from time 0 to time 1 is this push forward measure. Likewise, from time 0 to time 2. So now let's say as an artist, you input 3 keyframes the starting keyframe x0 and then two targets. Let's say the velocity field just points to the right uniformly, so it has these push forward frames. And obviously this doesn't satisfy the keyframe adherence criteria. So just like most graphics problems, we're going to fix this with a variational problem. We're going to choose a loss function to measure the deviation from the interpolated frame to the target keyframe. And then all we have to do is minimize the loss. It turns out that if you choose the loss function to be KL divergence, a very commonly used pseudometric between probability measures, and the problem becomes very similar to continuous normalizing flows in machine learning. So that's great. We can just minimize KL and we'll have our animation tool, right? Well, no, not exactly. There's a couple problems with this loss function. First, KL requires density access to evaluate. And at the beginning, as we said, we don't actually require density access for the keyframes. So this isn't necessarily available. But maybe that's not a big deal. After all, if the keyframes are normalized indicator functions, then we do usually have density values. So this is only a minor issue. The bigger problem with KL is that it's undefined if the two measures don't have overlapping support. And we can't possibly ask artists to draw keyframes that overlap each other. And this limitation is one of the reasons that in continuous normalizing flows, the first measure is a standard Gaussian, but that definitely won't work in the context of animation. So unfortunately, this popular loss function isn't suitable for this application. That brings us to the loss we actually use, the Wasserstein distance, which is intuitively speaking the minimum amount of effort needed to transport one measure into another. And there's a lot of really elegant math behind it, but for the purposes of this talk, it's enough to know that it's a metric on the space of measures, which only requires sample access and is well-defined even if the measures have no shared support. So with a few extra details in the paper, our keyframe fitting loss is essentially the Wasserstein distance. And this is where the Wasser in our project name Wassersplines comes from. The loss so far only cares about fitting keyframes, but since we're building an artistic tool for animation, we want to provide extra control over the trajectory. And so for that end, we build a couple different regularizers for the velocity field. There's no need to parse the equations. We're essentially just matching a type of physical behavior with pretty standard vector calculus expressions derived from the velocity field. These happen to achieve interesting effects on the animation, but of course it's important to have flexibility to add other regularizers based on the specific look an artist is trying to achieve. And that's one of the main benefits of using a neural parameterization for the velocity field. It's infinitely differentiable, and AutoDiff makes it super easy to build and test out new looks, new regularizers. This would be much harder to explore if you had to use, say, FEM-based functions or create new discretizations of every differential quantity of interest. The additional regularizers, though, mean that the fitting loss may not reach exactly zero because now they're competing. And so the push forward frames may not actually hit their target keyframes at the end of the optimization and or learning procedure. So we add a post-processing step to restore this strict keyframe adherence. And that works as follows. First, we start with the starting frame, advect it forward in time. Then we take the target keyframe and we advect it backwards in time. And for each time step where we need an interpolation frame, we compute a weighted blend of the forward and backward measures. This blending is a weighted Wasserstein barycenter, and it's computed once for each intermediate frame. And so this collection of barycenters is what makes the final animation, and it is guaranteed to hit all of the keyframes, even if the fitting loss is not zero. So now we'll show some results from our method and compare to other methods. There's some technicalities about the rendering, but I'll point you to the paper for those details. So here's just interpolations between horses and the Chinese character for horse. And our comparison here is against optimal transport maps, which is the cheapest way to move one mass distribution into another. Here's the frame by frame sequence, and I want to highlight that optimal transport really rips apart mass and takes points on the head of the horse character and maps it to the back of the horse, while our method prefers diffeomorphisms because it's parameterized by a velocity field. So it tries its best not to tear mass or space. Next, we'll try to make an animation of a fish swimming using a couple historical characters for fish in Chinese from 700 BC, 200 CE, and a modern day character. And this is the layout of the keyframes. So we're hoping that the characters will sort of swim into each other while transitioning. So left is a comparison with an existing trajectory inference method. Middle is our method. And they look really similar. Both produce plausible in-betweening frames for animation. But if I was the artist, I'd be, and speaking very subjectively here, I'd be a little unsatisfied because the fish are supposed to swim headfirst, while these animations look like they're kind of translating into position and then squashing. So to fix that, we can add a curl-based regularizer, and now you see the velocity field is promoted to rotate keyframes. Here's another example where we animate from a butterfly to a cat to a caterpillar. Left is our method with no regularizers, while on the right, we add a user-specified desire that they want a more circuitous trajectory. And then it turns out that with minor changes to the network structure, we can force a cyclic behavior in time. And so we can create loops like this. And so this is the definitely accurate life cycle of a butterfly. Here's an animation showing effects of various regularizers on the same sequence of 4 keyframes. And it may be hard to digest all of these now. I'll just say the important thing is they're all a little different. And I'll point 2 of them out specifically. This is the result of our method with acceleration-based regularization compared to consecutive optimal transport maps. You can see that our method has smooth, seamless interpolations at the keyframes, while the consecutive optimal transport maps has really sharp corners. And this is analogous to the difference between splines and polylines. So that's why our method is called Wassersplines rather than poly-Wasserstein geodesics. Also, Wassersplines is much easier to say. Here's some 3D results of a hand closing into a fist that then transforms into a cat. Okay, so the video is a little fast, but here's a specific frame I wanted to point out. You may have noticed some blobby artifacts in between fingers, and that's because of this mass transferring effect. And if, as an artist, if you're okay with that, then there's no problem. But personally, I find it a little unsatisfying that the space between fingers isn't clear. And the reason this happens is because when you compute Wasserstein barycenter interpolation, there's always a mass preservation term. And that's a hard constraint, which means if a finger is thicker in one keyframe than the next, then it has to bleed mass into adjacent fingers. There's an easy fix for this. We'll just use unbalanced barycenters instead. And the key difference is we take that hard mass constraint, mass preservation constraint, and make it a soft constraint instead. And so here is the afflicted frames. You'll see on the bottom, once you use unbalanced barycenters, there's no more bleeding of mass between fingers. Here's 2 rings that rotate, and there are a couple detailed stripe patterns that fade in and out. On the left, I've added rigidity-based regularization, and on the right, there is no rigidity regularizing. And so you can see the effect of rigidity is that it makes the animation more tame, even though it's impossible for it to be completely rigid because that would erase all of the spiraling details. And finally, it wouldn't be a graphics paper if there wasn't a cow turning into a sphere somehow. So here you go. Okay, so we've formalized the unstructured animation problem, proposed a solution, but there's always room for improvement. First, I think the expressiveness could be explored further. These are just regularizers I made up, but if you're an artist and you want to achieve a certain look, you'll probably want custom regularizers. Second, if the fitting loss really could reach 0, we wouldn't need this barycenter step at all. And so getting a better fit accuracy is important. Hopefully that was interesting or at least entertaining. And now I'll be happy to take any questions.
Thank you. Doesn't work anymore. All right. Thanks a lot for the very nice presentation and your work. Do we have some question in the audience? So I will start with one if some people want to think about it. I was wondering in your regularizer, when you were talking about having more artistic control, would it be possible to have local regularizer, like locally in space or locally in time, to have something that rotates at some time and then have another behavior afterwards?
Yes, in short, definitely. And we actually already do regularize locally in space because we don't want uniform curl all over the vector field. We really only want it to apply to where the mass actually is. And so these regularizers are integrated where the measure is. It's integrating according to the measure. And that's a detail I glossed over, but it's in the paper. And you can localize it in time as well if you wanted.
Okay, great. And then also about the control of the results, like when you show the cow that transforms into donuts, could you have a way to control where the change of topology is going to happen? At some point, the cow was having a hole in the middle of its shape. Could we enforce the fact that maybe the cow have its head going to merge toward its feet instead?
That's a really interesting idea. I don't have an immediate idea for how to do that, but what vaguely comes to mind is you could add a metric that says it's harder to transport mass on this part of the cow than it is over here. And so that would essentially shift the center of mass. If you create a different metric on the space, then the center of mass of the cow is no longer its like visual center. And so that might achieve this kind of effect. I'm not sure how well it would work. That would be interesting.
All right, great. Last chance for the audience. No question? Okay, I think we can all thank you again.